Welcome. This is Mrs. Greathouse. Today we're going to start talking about how those electrons are arranged in the atoms, and we're going to learn how to make electron configurations. Have you ever been out west where there are these beautiful red rocks? Many of them are in very interesting configurations. What would happen if this rock tumbled over? Okay, it would fall to a more stable position, but it would have less energy. A lot of times our electrons work in the same way. Okay, so our electrons are arranged in the different orbitals around the nucleus. Okay, we talked about those yesterday. When we write out an address for where each electron is, these are called electron configurations. Okay, we have 3 rules on how to make electron configurations. Okay, the first one is the Aufbau principle. The second one is the Pauli exclusion principle. The third one is Hund's rule. Okay, and I will go through each one of these separately. Okay, according to the Aufbau principle, electrons occupy the orbitals of the lowest energy level first. We are going to work with diagrams like you see here. Okay, each box is going to represent an orbital. Aufbau says we have to start with the lowest energy, so we are going to start at the bottom. Okay, notice there are numbers and letters here. Okay, like we talked about previously, the S block has a maximum of 2 electrons. So there can be 2 electrons in each box. Okay, our level 2 orbital can have a maximum of 8 electrons. Okay, 2 electrons in each box. What do we say for level 3? How many can be there? 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, and if we look at all the level 4s, we said there could be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so this connects to what we did yesterday, the different levels, different numbers of electrons at each level. Okay, when we use this Aufbau diagram, we can put 2 electrons in each box to show a full orbital. Okay, second rule, Pauli exclusion principle. Okay, an atomic orbital may describe at most 2 electrons. Again, 2 electrons in each box. To occupy the same orbital, the 2 electrons must have opposite spins. So you're going to have one spinning clockwise and one spinning counterclockwise. Okay, and we're going to show this when we make our configuration with up and down arrows. Okay, last rule. Hund's rule tells us that our electrons are going to occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. Okay, so we're going to set all our electrons to spinning clockwise, okay, before we add electrons that are spinning counterclockwise. So when we fill up an energy level, okay, we are going to make sure all our arrows are going in the same direction and fill up that level before we switch the direction of our arrow. Okay, so here are some examples of some electron configurations over here. Okay, here's your element. Hydrogen has 1 electron. It's going to go in the first box. Okay, we show it with an arrow going up. Okay, helium, 2 electrons. We have to start at our lowest level. We have to give our spins opposite directions. So the first one clockwise, the second one counterclockwise. We have to fill this lowest energy level before we would start here. Okay, lithium has 3 electrons, atomic number 3 electrons. Notice that we fill up clockwise, counterclockwise, and energy level 1 first before we add that 3rd electron in energy level 2. Okay, let's look down here at oxygen. Oxygen's atomic number 8. It'll have 8 protons, 8 electrons. Okay, first 1, 2. Then we go 3, 4, 5, 6 to fill up all of our 2p orbitals. Then we come back and add our opposite spin for 7 and 8. Okay, when we write our electron configuration, our address of where electrons are, we say 1s2. Okay, there's 2 electrons in the 1s box. 2s2, 2 electrons here. 2p4. Okay, in our p orbital, we have 4 electrons. So 1s2, 2s2, 2p4 is the electron configuration of oxygen. What do you notice about all these superscripts? Okay, what happens if we add them up? 2 plus 2 plus 4 is 8. Okay, that should equal our atomic number, and that's going to be a great double check for us. Okay. Okay, you are going to receive a handout with these diagrams on it. You will be able to use it for homework and test, but you need to know how to use it. Alright, the trick is follow the arrows and the lines. Notice that 1s2, follow this little thin line here, then to 2s2, then to 2p, then to 3s, 3p. Okay, it all makes sense so far, but now we're going to go out of order. Now we're going to go down to 3p, 4s, back to 3d, 4p, 5s, 4d, 5p, and so on. And you might wonder why. Why do we go out of order? It's because the 4s orbital has a lower energy level than our 3d. Okay, same, and that pattern continues, and if we look at our Aufbau diagram, that shows it as well in the boxes, and it shows that the 4s box is a little bit lower than our 3D box. Okay, another trick here. How does this correspond? If we look at our periodic table, okay, our first 2 rows are what are in our S block. So if we are writing an electron configuration for magnesium, okay, our S block is going to be full at the 1, 2, 3rd level. Okay, here's your P block. Your D block is actually in the middle of the periodic table. Okay, and the F block is underneath, but actually fits in part of the D block. Okay, so we'll work more with this in class, and you'll have your very own handout. Just note that you are going to follow the arrows and the narrow lines. Okay, and they don't always go in numerical order. Alright, so I think we're ready to try one. let's write the electron configuration for phosphorus. Okay, so here we go. Phosphorus, we have to know its atomic number, so we know how many electrons it has. It has 15. So first, we're going to fill up our S box. 1, 2. Hang on, I'm going to switch technology here. Okay, electron configuration of phosphorus. Let's try it. It's got 15 electrons. So 1. No, that's not what I wanted to do either. Okay, here we go. So 1, 2. Give it the opposite spin. Now I can go to energy level 2 because that one's full. 3, 4. Fill up my S. 5, 6, 7. Get all the spins going the same way. 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I'm going to ready to write my electron configuration now. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p3. Okay, double check me. Do all my superscripts add up to 15? Sure, they do. Enough. So all I had to do to write my electron configuration was go back and see how many arrows I had in each box. Okay, let's try a couple more. Let's try boron and silicon. Okay, boron's atomic number is 5. Let's take a look at that. We're going to go 1, 2, 3, 4, 5. Electron configuration 1s2, 2s2, 2p1. That's all there is to it. Let's try one more. Okay, electron configuration of silicon. Silicon's atomic number is 14. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Notice how we're following all 3 rules. Start at the lowest level. Each box has opposite spin. Get everything spinning in one direction before you start the other direction. Okay, so now let's write our electron configuration. 1s2, 2s2, 2p6, 3s2, 3p2. Double check. Does it add up to 14? Sure enough. Okay, we got those rules and they're fantastic. But as in many things, there's always exceptions to the rules. Sometimes there's a couple elements that aren't going to follow the rules because they are more stable with a half-filled sublevel than with a full sublevel. Okay. Copper is one of those exceptions. Okay, what we would expect for chromium and copper are the electron configurations on the top. But what is correct is the electron configuration at the bottom. Notice that this 4s orbital is only half full versus 4s2. Okay, it's actually going to be more stable here, okay, than here. So those are the only 2 exceptions to the rules that you need to know. Okay, so make a summary. We'll practice in class. Thanks for listening.